Hey everyone, welcome back to the channel. Today we are building the Black-Scholes option price model from scratch in Python. And starting with a quick bit of context, this model was introduced in 1973 and changed everything by providing an equation for European option prices. It became the backbone of the modern derivatives market, and Scholes-Merton won the Nobel Prize for it in 1997. Well, it's not perfect because it assumes constant volatility, log no returns, and a series of other assumptions, but still the golden standard for pricing European options and getting the implied volatility from it. Well, so getting deep into the model, for those who are not familiar with Black-Scholes, it comes from stochastic calculus. And if you analyze well the equation, the call price is basically what I expect to be the final underlying price minus the exercise price. And it's important to understand what is ND1 and ND2 by these equations. ND2 is basically the risk not probability that the option finishes in the money. ND1, I would call it the options delta if the dividend is you expect to be zero. So what is this delta saying is basically the sensibility of option prices according to the change in the underlying price. So for example, a delta of 0.3 is the option is out of the money, and in the underlying price changes in the underlying price won't affect a lot the price of the option. And if you get like a high delta, like a 0.6, changes the underlying price will affect a lot the price of the option. So let's code. So for the coding part, this is quite simple. I'm just using the NumPy and the SciPy optimized libraries, and these are my inputs. This is an example of an add the money call. And for building the functions, I'm using something called the modular approach. So instead of building one unique function, I'm building small functions, and then I'm gonna call these small functions to build a larger one. So D1 and D2, which are basically the formula that was shown. D2 is basically D1 minus the standard deviation times the square root of the t. And from that, we have the Black-Scholes function. So here are the previous functions I've built, and those are the conditionals because, as it was shown, the call option and the put options have a kind of inverse formulas, and also another condition of error in case there's no option type, and then I get the price. So let's start playing with it. So I basically all these functions I built, I I call them, and to get ND1 and D2, I want the normal distribution of it. So I use this function from the stat tools to get it. And well, this is the price of the option, $10. And well, let's start playing with the volatility. I can play with any variable I want. So let's say 0.3 volatility. You see price increases. This is because the higher the volatility, the higher the option price. But it's nice to see the dynamic of the ND1 and ND2, like how they're changing. As you see, from 0.2 to 0.3, the ND1 is decreasing a bit, but the ND2 is decreasing a lot more because of this other variable of the minus standard deviation. But as I keep increasing the implied volatility, you can see the dynamics of these variables. So this is nice to keep playing with those variables and see what is happening with the function. The next step will be to calculate the implied volatility driven by market prices. And the first thing we should do is calculate our boundaries. Why? Because if the market price is out of these boundaries, it won't be possible to calculate the implied volatility because it's a violation of the Black-Scholes model. So basically, what are those boundaries? Well, it's the intrinsic value discounted by time value. Well, this is like an European option. So when you have like a high intrinsic value, you need to discount it because you cannot exercise at this time. So it's basically, well, it's the stock price discounted by dividends and the exercise price discounted by time value. So the lower up of the boundary condition is basically this intrinsic value discounted, and the upper value is the discounted price of the stock. Well, I established this function here called price bounds, and I give the value for these two variables called lower and upper. So the lower bound 4.8 and the Black-Scholes price is 21 and the upper bound is 100. So the Black-Scholes price respect these boundaries. If the price was like 2, it wouldn't be possible to calculate. So yeah, let's move to the next step to calculate the implied volatility. And how is it calculated? Well, it's basically you have the Black-Scholes function, you see, and you do a solver to get this because you already have the price, you have the market price. And from this formula, you need to get this. And for that, you need to use something called a Brent solver from the SciPy library. And it's doing, well, let's first check if our market price is between the boundary conditions. In case it's not, I'm gonna give an error message. And okay, if it's everything fine, okay, I'm gonna define an objective function that the return basically the Black-Scholes price minus the market price. And the sigma, this is basically a function of the brain in which I derive the implied volatility from the market price. This is what returns to me. So like I'm gonna give some examples. If I get the market price of 10 and all the other assumptions, the inputs we had here, what is gonna be the implied volatility? Well, it's gonna be 0.18. If I have 8 of market price, boom, 0.13. Now imagine if I have a very low market price that is far below the present value of the intrinsic price. Well, it's going to give an error to me because it violates the bound. Well, I can play between the boundaries like 20, 0.45, 50, like 250 is also going to give an error because it's higher than 100. See? So these boundaries need to be respected. And for the last part, this is my website. I made a Black-Scholes implied volatility calculator derived from this Python script. So here you can basically play with all these variables. This is to specify an option. So for example, this is alt the money call. So it's going to be cheaper. If I have an at the money call, it's going to be more expensive. And I start to play with the volatility. I have a 30 of volatility for how it's going to increase. And I also play with the time value. Like let's see, that is like a shorter term option 0.5 or even lower 0.2 if you want to play with short term options. And well, there's like a series of implications with all these variables. This is why you use the Greeks. But for now, we're just playing with these variables and see how they change the Black-Scholes model. And this is the implied volatility solver. Well, what is the difference here? I put the option market price. So, for example, I open Bloomberg, FactSet, or Yahoo Finance, or any data provider, and I see an option. Okay, this option right now is costing 10 bucks. We'll be more realistic. We'll say like a 3.6. Like it won't be equal to the option premium, but let's see similar. And I have already all these inputs. I'm considering all these inputs like what's going to be the implied volatility from it. So 38, 20, 38.22, 28% of implied volatility. And okay, let's change a bit these variables. Let's put like a 10 of time to maturity. You see, the the boundaries changed because I changed the time. You see what's gonna happen? Well, it's not gonna calculate. But I put something interesting in this calculator. Instead of like just giving an error message and not running, this automatically will go to the lower bound. It automatically changed the price to lower bound feature. So it runs anyway, just for you to take into consideration. Instead of not doing anything, they change the value to have, okay, what would be the market price, the lower bound, and how it's going to be the implied volatility. It's going to be like a minimum, basically next to 0. So let's put like 20 here of market price, 18. And like, let's see, I want to put like some dividend yields. Well, we also changed the boundary conditions, but I'm going to still be able to run it. So this is important. You should always know the implied volatility, the lower and the upper bound. So you have no mistakes when you calculate the implied volatility from the Black-Scholes model. And here in this calculator, there is also an explanation in the details of some variables, and you can use it to make some simulations or specify options. And of course, the option premium calculator here will be different from market price because there's Black-Scholes is a model and it has its assumptions. So don't count that it's gonna be maybe if you have like at the money options, it might be more closely, but out the money when you have like skill, well, it's gonna be quite different. So don't take this into consideration to, oh, this is different from Black-Scholes as well. It's expected to be different. But still the market uses a lot Black-Scholes to get the implied volatility from market prices. So this might be, I believe, more useful. So that's the video, and I hope you enjoyed and learned from it.